Okay, so let's get started. So today, this is going to be a lecture, so no tutorial, but I remind you the assignment is due tomorrow. So let's start with a summary of relevant things we need to know for today's lecture. So we've been working with the Hamiltonian. And the Hamiltonian depends on the generalized coordinates, their conjugate momenta, and potentially time. We call these things, Q's and P's, canonical variables. And they obey the equations of motion that are given by Hamilton's canonical equations. So if we want to know how Qi evolves with time, then we need to know Qi dot, and that's given by the partial derivative of the Hamiltonian with respect to the conjugate momentum. Similarly, for Pi dot, that's given by minus the partial derivative of the Hamiltonian with respect to Qi. We introduced Poisson brackets last week, and hopefully you've gotten some practice with them during the assignment this week. There's some weird behavior of my tablet here. I hope it doesn't go crazy. So Poisson bracket is a thing that's defined between two functions of the canonical variables. So the definition of the Poisson bracket of two functions u and v, where u and v are functions of q and p, the Poisson bracket is defined to be a sum over the degrees of freedom of di u by di qi times di v by di pi minus, the other way around, di u by di pi, di v by di qi. And we saw these Poisson brackets have a bunch of properties, some of which you were asked to prove in the assignment that's due tomorrow. On Tuesday, we looked at canonical transformations. Canonical transformations are transformations from your original set of canonical variables Qi and Pi to a new set, which we've denoted with capital Qi and capital Pi. Now, a specific case of canonical transformation is what we call point transformation, and that's where you only change the q's. So that's like saying, I can describe a physical system in either Cartesian coordinates or spherical coordinates. I'm allowed to describe the system in two different coordinate systems, and I should get the same answer. That's a point transformation, because you're only changing the q's. Canonical transformation is a more general version of that transformation. You're allowed to change the p's as well. And in fact, as we saw, you can change them in very general ways. In fact, we looked at specific examples where we had a transformation that basically changed the labels of q's and p's. So the q's became p's and the p's became q's. And the laws of the equations of motion were preserved. And what I really mean there is that if you have an initial coordinate system, lowercase q and p, then you have a Hamiltonian qi and the pi, and potentially t. In the transform coordinate system, you have to reevaluate the Hamiltonian, and that we've been calling it capital K, and so that depends on capital QI and capital PI time, potentially. The transformation is canonical if is it refreshing? Am I frozen, or can you guys still hear me and see me? Do you guys hear me at all, or?
I can hear you.
It looks frozen on my other computer. Okay. All right. So, and can you see the last thing I wrote is canonical if? Because when I look on my other computer, it doesn't show the whole thing anymore. That's weird. Yep, okay. Oh, well, my other computer got kicked out. All right, there we go. So I think it was just my one computer. Just give me a sec here. Close my browser. Yes, hold on, I'm just trying to lower my usage of the internet. All right, hopefully that'll be better. All right, apologize for that. So, canonical transformations from lowercase q's and p's to capital Q's and p's, you transform the Hamiltonian. That transformation is said to be canonical if in the new transformed coordinates, the new coordinates obey the canonical equations. By that I mean that it's still true that capital QI dot, capital QI dot, if that's equal to di K by di Pi, capital Pi, and capital Pi dot is equal to minus di K by di Qi. So it's a canonical transformation if in the new coordinates and the new Hamiltonian, the canonical equations are still satisfied. So if I give you a transformation from Q's and P's to capital Q's and capital P's, how do you know if it's canonical? So clearly there's an annoying way to do that, which is to then calculate the transformed Hamiltonian, calculate the equations of motion, and see if they follow the canonical equations. All right. So that's a little bit cumbersome, you can imagine. So what we'll see today is that Poisson brackets give us a really, really easy way to tell if a transformation is canonical. So in general, we found that the canonical transformation, a canonical transformation can be given by specifying a generating function. What we call a generating function. And we call that function capital F. The F depends on a mix of the new and old coordinates. So by new I mean capital letters, and by old I mean lowercase letters. And there's 4 possible combinations that you can do. So for example, we can have a transformation of what's called the second type. So there was 4 types, right? And they're written in your notes. You're welcome to go look them up again. But let me write down the case of the second type, where F is given by a function f2 that depends on the lowercase qi's and the capital Pi's and t. And then to make things cancel out nicely, you have to put into the transformation the sum over qi and pi capital. So we saw that you can just specify a canonical transformation by giving this so-called generating function. The transformation is then, so f depends on the lowercase q and the capital P, so then we need to know, how do I find the capital Q and the lowercase p from f? And for transformation of the second type, we saw that the transformation equations were that lowercase pi is di f2 by di qi. And we saw that the capital Qi was given by di f2 by capital Pi. So given f and these 2 equations, then you can figure out exactly what the mapping is from lowercase q's and p's to capital Q's and p's. And we did a couple of examples of that. Okay, so any questions? So far we know that if I give you a function f that depends on a mix of the new and old coordinates, then you can apply these transformation equations, and the transformation is guaranteed to be canonical. But if I don't give you f, and I just give you the transformation from the lowercase variables to the capital variables, then it's going to be a pain for you to figure out if that's actually a canonical transformation, because you're going to have to calculate the new Hamiltonian and then see if it satisfies the canonical equations. So we're going to see today a method using Poisson brackets that makes that much easier. And then we're going to extend that and use some of the properties of Poisson brackets to blow your minds with a deep insight into classical mechanics. But to get there, we have to do a lot of math. This is probably the worst lecture of the whole course in terms of math. But it's not difficult, it's just painful, because there's a lot of sums and indices everywhere. So, might as well start on a new page, I think. So Poisson brackets and canonical transformations. Now let's stop writing canonical transformation each time. I'll say CT. In fact, I'm going to stop writing Poisson bracket all the time and say PV. So consider the case of a time invariant to make things easier. Consider the case of a time invariant canonical transformation. I guess that brings up the point here that I forgot to say, that the new Hamiltonian capital K is given by the old Hamiltonian plus the time derivative of that generating function, the partial time derivative of that generating function. So if that generating function doesn't depend on t, then the new Hamiltonian K is equal to the old Hamiltonian H. So that's what I mean by a time invariant canonical transformation. So because the Hamiltonian is unchanged, then the new coordinates, because the transformation is canonical, obey the canonical equations, right? Namely, capital QI dot is equal to the derivative of the partial derivative of the Hamiltonian with respect to pi. And similarly, capital PI dot is given by minus the partial derivative of the Hamiltonian with respect to capital QI. Okay, so far so good. Now remember, the Hamiltonian H, or K, it's literally the same thing. I can think of H as a function of the capital Q's and the capital P's, right? So if I think of H as a function of the capital Q's and the capital P's, now remember, it's a time invariant situation, so I'm going to ignore time, and then it turns out it also works if you don't ignore time, right? I don't want to carry that extra term around everywhere. So if I consider H as a function of capital Q's and capital P's, if I do di H by di Pi, I can use the chain rule. And so let me write that out a little bit more clearly. So H is a function of the capital Q's and the capital P's, right? The capital Q's and the capital P's are themselves functions of the lowercase q's and the lowercase p's. All right, so when I do di H by di Pi, I can think of H as actually being a function of the lowercase q's and p's. And so I can also think of H being a function of the lowercase q's that depend on the uppercase letters, and same with the p's. These are all saying the same thing. They're saying the Hamiltonian depends on either lowercase or uppercase variables, and then those lowercase or uppercase variables depend on the other kind of variables. So in the first line, I'm actually going to assume that, let's say I've written H in terms of the lowercase variables. Right, so let's say this is H lowercase q and lowercase p. So it's exactly the same as if I say capital Q and capital P. But if I think of it as being a function of lowercase q and lowercase p, then when I do this partial derivative, I need to do the chain rule. And so then I have to do the sum over all the degrees of freedom. So then I take di H by di Qj, and then I multiply that by di Qj by di Pi. Right, that's just the chain rule. And similarly, then I have a second term, which is going to be di H by di lowercase pj times di lowercase pj by di capital Pi. That's just the chain rule. It's the same thing for the other one. For capital PI, I can write that as the sum of the degrees of freedom. Put the minus sign in front, then I have di H by di Qj, di Qj by di capital Qi, plus di H by di Pj, di Pj by di capital Qi. All right? Okay. Now let's go the other way around. Let's think of Qi is a function of lowercase qi and lowercase pi. And similarly, I'll think of pi as a function of the lowercase qi and the lowercase pi. So if I do qi dot, so d capital Qi by dt, then I have to do the sum over j. So I'm thinking of qi as a function of lowercase q's and p's. So again, I have to do a chain rule. So if I do the chain rule here, I have the sum. So first, I have di qi by di lowercase qi dot. Right? And plus di capital Qi by di, sorry, that should be a pj because it's the sum. So it's a lowercase qj and a lowercase pj dot. That's just the chain rule. We've done this several times, right? Now I can insert the canonical equations in there, because I have a qj dot and I have a pj dot. And qj dot is given by the canonical equation, and so is pj dot. So that becomes the sum over, so I have di capital Qi by di lowercase qj. Instead of qj dot, I'm going to write that as di h by di pj. I have a minus sign, and I have di capital Qi by di lowercase pj, and then the pj dot is minus di h by di qj. So I already put the minus sign there. And so it's equal to that. I can do the same thing to pi dot. Right? I can think of pi dot as a function of lowercase q and lowercase p. So if I write pi dot with the chain rule, I have the sum over all the variables that pi depends on. So I have di pi by di qj, dqj by dt, which we call qj dot, plus di pi by di lowercase pj dot. And then again, I can insert the canonical equations there to get rid of the qj dot and the pj dot. So I have di capital Pi by di lowercase qj, and in qj dot I replace by di h by di pj. And the second term is going to be a minus sign. Then it's di pi by di lowercase pj, and then pj dot from the canonical equation, that's di h by di qj with a minus sign, which I already put in. Okay? Now, I actually have two different ways of writing qi dot, capital Qi dot, and capital Pi dot. So those two things must be equal, right? And since they're equal, the various terms must be equal to each other. So let me pick out for example, di h by di qj in the first expression for qi dot, and I see it appears again down here in the alternative expression. So the thing in front of it, or the thing that's with it, must be equal in the two expressions. So in the top expression, the thing that I have with it is di lowercase qj by di capital Pi, di lowercase qj by di capital Pi. That's got to equal to the thing I have in the second expression. In the second expression, I have a minus sign, as I have a di capital Qi by di lowercase qj. That's incorrect, actually. Let me work this through in the notes here. I think I did it right in the notes, but wrong. Di qj by di pi. Oh, I just wrote it down wrong here. In the second expression, that's a pj, not a qj. So these two things must be equal to each other. Everybody okay with that? So let me pick another one. Let me pick the di h by di pj in the qi dot term from the bottom. I have to look for it at the top. It's right here. So the thing that goes with it at the top is di lowercase pj by di capital Pi, di lowercase pj by di capital Pi. Let's see, put on here. Try to make my lowercase p and uppercase p different. So in the top one we have di lowercase pj by di capital Pi, and in the bottom term we have di capital Qi by di lowercase qj. Yep, so let me write that in a, so you get the idea. So this gives four equations that are called the direct conditions. So those four equations, so I'll rewrite the two that I just wrote, and then you're convinced that I can make two more by looking at the di h by di whatever in the pi terms, right? So that'll give me four equations. The four equations are di lowercase pj by di capital Pi is equal to di capital Qi by di lowercase pj. Second equation is di lowercase qj by di capital Pi is equal to minus di capital Qi by di lowercase pj. The third equation is di lowercase qj by di capital Qi equals di capital Pi by di lowercase pj. And the fourth equation is di lowercase pj by di capital Qi equals minus di capital Pi by di lowercase qj. So before I explain this a little bit, there's a bit of a pattern in them, but it's not super obvious what the pattern is. The one thing that's going on in the pattern is that if I have di lowercase letter by di capital case letter, that's equal to di capital case letter by di lowercase letter, right? So if you have an uppercase on the top and a lowercase on the bottom, on the left-hand side of the equation sign, that's the opposite on the other side. The other thing that keeps flipping from one side to the other is the index I and j. If I have j on top and I on the bottom, I have I on top and j on the bottom on the right. If on the left, j is at the top, on the right, j is at the bottom. Then I have the final pattern is that if I have on the left-hand side di q by di q, and on the right-hand side I'm going to have a positive sign. So if I have the same letters of the alphabet, so P's and P's, or like lowercase p's and uppercase p's, or lowercase q's and uppercase q's, if I have the same letters of the alphabet on the left-hand side, then on the right-hand side I have a plus sign. And if I'm mixing letters of the alphabet, then I have a minus sign. So the second and fourth equations have a minus sign. So those are completely arbitrary rules that I'll use later, so I won't have to memorize the equations. Okay. So what are these direct conditions? Well, what did we assume when we did this? These equations are relating a specific coordinate in one system to another coordinate in the other system, right? So it's like these are true for specific values of I and j, right? So it's like di lowercase p2 by di uppercase p1 for the first equation. That would be equal to di capital Q1 by di lowercase p2. Oh, I wrote it down wrong. That's a QJ. The first one I wrote down wrong. I just don't want to write it down correctly. Okay? So we assume that the transformation from the lowercase q's to the uppercase q's and p's was canonical. Right, we put in the canonical equations, the di h by di q equals to I dot. So you can turn this around and you can say that these are the conditions on the transformation for it to be canonical. So if I gave you a transformation from lowercase q's to capital Q's and p's, you can do all these partial derivatives between all of the q's and all of the p's, and if they're all true, then the transformation is canonical. So you can use these relations, and use these conditions to check if a transformation is canonical. That's why they're called the direct conditions. You can directly check if the transformation is canonical by doing all of these partial derivatives. There's not just four of them, right? It's 4 times the number of degrees of freedom. So that's certainly a pain to do. But for sure it works. It's straightforward. So there's a lot of partial derivatives of q's and p's. And so plus one brackets have a lot of partial derivatives of q's and p's, so maybe they can help us here. And so indeed they can. So let's consider the Poisson bracket of the lowercase variables. So let's say, let's consider the Poisson bracket of, for example, lowercase qj, or lowercase qi, let's say, with lowercase qj. Evaluated in the capital Q's and P's. So remember, we can take the Poisson bracket of lowercase qi with lowercase qj, as we've done before, using the lowercase q's and the lowercase p's. In fact, you showed, or you're showing the assignment, that the Poisson bracket of qi and lowercase qj is equal to 0. Right? The only Poisson bracket that's non-zero is qi with pi. But that's if I evaluate the Poisson bracket in the coordinates lowercase q and lowercase p. It's not guaranteed that it's going to be equal to 0 if I evaluate it in the capital Q and the capital P. So what do I mean by that? What I mean is that we consider qi now, lowercase qi, to be just some function of the capital Q's and P's, and we think of the qj as some other function of the capital QI's and capital P's. And so forget that the Q and J's are canonical variables in their own coordinate system. Because we have transformation equations to go back and forth, there exists a function that gives the Q's in terms of the capital Q's and capital P's. So these little lowercase q's are functions of the capital Q's and P's, and so we can evaluate the Poisson brackets of them. So let's go and try that. So let's do the Poisson bracket of lowercase, I have to follow the notes, so I screw up all the indices here. The lowercase qi with the lowercase qj. I'm going to put a little index at the bottom here to say I'm evaluating it in the coordinates capital Q and capital P. So that means I have to apply the definition of the Poisson bracket. So I already have two indices I and j, and I have to do in the Poisson bracket a sum, right? So I need a third index, which I'm going to call k. So the Poisson bracket is die of the first function, which is lowercase qi, by die capital Qk. Then it's die lowercase qj by die capital Pk. And it's minus die qi by die capital Pk times die qj by die capital Qk. Right, that's the Poisson bracket. So that's equal to, I'm going to use my direct conditions now to get rid of some of the terms. Namely, I'm going to get rid of the die qj by die pk. So I'm going to get rid of, I'm going to apply the direct condition to this red term. So let me write out the first term. So I have die lowercase qi by die capital Qk. So the red term, it's a lowercase q over a capital P. So a lowercase q over capital P is this one, right? So if I use that direct condition, so I have a lowercase qj over capital P, so that needs to be a capital Q over a lowercase p. It's going to have a minus sign. Now, if I look at the indices, I have to flip. So it goes from, on the top, it goes from j on top and I on the bottom to I on top and j on the bottom. So that means I have to have qk on the top and I on the bottom. Whoops, no, that's wrong. I was looking at the wrong one. I have to look in what I've circled here in red. So I have to bring the k at the top, and I have to bring the j at the bottom. Everybody okay with that? Do the same thing with the other term. So the other term is minus di qi. I'm going to keep the di qi by di capital pk. And then the term I'm going to swap out using the direct conditions is this term here. I need a lowercase q over a capital Q. If I look at my direct conditions, it's the third equation. That has a lowercase q over a capital Q. So applying the direct condition, that's going to give me a capital P over a lowercase p. And then I have to switch the indices. So in the blue circled thing here at the top, or just above, I have lowercase qj. Hello? Okay, people can hear me now? Alright. I think you caught most of what I said recently, right? You guys can still hear me. That's a pretty good stretch without technical issues. Okay, so I applied the direct conditions to transform the red and blue terms. And it's hard to keep track of because if you keep switching uppercase and lowercase letters and indices. But I'm pretty sure I did it right. So then I have two terms in my sum. They're both negative. So I'm going to factor the minus sign out. And then I'm going to write this as, just basically rewrite it. So I have di lowercase qi by di capital qk times di capital qk by di lowercase pj. And then plus, you're going to factor out the minus sign, di lowercase qi by di capital pk. And the second term is di capital pk by di lowercase pj. So that actually does look familiar. That is just the chain rule, right? That is actually equal to minus di lowercase qi by di lowercase pj. Right? Because if, let's say I started from the last line. Let's say I want to calculate di qi by di pj. And I claim that now lowercase qi depends on the capital Q's and the capital P's. So if I want to do di by di pj of lowercase qi, and I'm thinking of lowercase qi as depending on capital Q's and P's, then I have to apply the chain rule. So I have to sum over all the things that lowercase qi depends on. And when I do that, I get exactly the equation that's above it. Right, so that's like, In the first term I have di lowercase qi by di capital qk, and then di capital qk by di pj, and then the second one I have di qi by di capital pk, di pk by di pj, summed over all k's. That is exactly like saying di qi by di pj. But now di qi by di pj, we also know that's equal to 0 because qi and pj are independent coordinates in untransformed frame. So that's got to equal 0. Alright, so then we have two more options that we can do. We can do similarly. I can evaluate the Poisson bracket of lowercase pi with lowercase pj in the new transform coordinates q and p. So that means I have to do the sum over k of di pi by di q capital qk by lowercase pj by di capital pk minus the other way around. I have di lowercase pi by di capital pk times di lowercase pj by di capital qk. So I can then insert the direct conditions to get rid of some of the variables. So in this particular case, you would want to get rid of this guy and this guy. And then the math is exactly the same and confusing. And so what you find in the end, that's going to be equal to di lowercase pi by di lowercase qj, and that's equal to 0. It's exactly the same math. I'm not going to, it's painful. You saw how painful it was, but it's doable. And lastly, we can evaluate lowercase qi, Poisson bracketed with lowercase pj. And then what you'll find there, you'll find that that's going to be equal to di lowercase qj. Oops, di lowercase qi, sorry. Di lowercase qi by di lowercase qj. And that's equal to 0 unless I equals to j. And we call that the Kronecker delta. So we've evaluated 3 different Poisson brackets. We evaluated lowercase qi with lowercase qj in the capital Q's and capital P's, and we found that was equal to 0. Then we did it with lowercase pi and lowercase pj, and we found that was equal to 0. And then we did it with lowercase qi and lowercase pj, and then that was equal to delta ij. So now, that's exactly what those Poisson brackets are equal to when evaluated in the lowercase and lowercase q's and lowercase p's. So the Poisson brackets between coordinates are preserved by the canonical transformation, or by a canonical transformation, because of the direct condition. So all that is just to say this. If I take the Poisson bracket of lowercase qi and lowercase qj, and I evaluate it in the transform coordinates capital Q and capital P, I get exactly the same result as if I had evaluated it in the untransformed coordinates Q and P. And so what we find is that between the coordinates, so Qi and Pj, let's say, evaluated in Q and P, that would be the same as lowercase qi, lowercase pj, evaluating the initial coordinates, like delta ij. And similarly for the pi with the pj, that's equal to what you got originally, pi and pj. So it turns out you don't need to put the little indices at the bottom of the Poisson bracket. At least we've shown it between Poisson brackets of the coordinates. It doesn't depend in which coordinate system you evaluate the Poisson brackets. So you don't need to keep writing those indices. And it turns out this gives us a very good way to check if a transformation is canonical. So you can easily verify if the transformation is canonical. So you have a transformation from lowercase q's and p's to capital Q's and p's. Then, if you evaluate the Poisson bracket of capital Qi with capital Pj, that must equal delta ij. And you can evaluate that Poisson bracket in whatever coordinate system is most convenient for you. So that Poisson bracket is delta ij, and the Poisson bracket of Qi with the Qj, that has to be equal to the same Poisson bracket of, say, a capital Pi with a capital Pj, and that's equal to 0. So given the equations for Q's and P's, you can then evaluate the Poisson brackets. It doesn't matter which coordinate system you use to evaluate the Poisson brackets. And if you find that the Poisson bracket between a Qi and a Pj is delta ij, and all the other ones are 0, then the transformation is canonical. And that's a much, much easier way to verify if a transformation is canonical. I'll just do a very trivial example. Say it's 4 in the notes. And I'll do just a morning assignment next week. So let's show that the transformation given by capital Q is given by lowercase p, and capital P is given by lowercase q. Let's show that that is canonical. So here we have one degree of freedom. Right, so there's only one Q and one P. And the transformation says that the new Q is given by the old P, and the new P is given by negative of the old Q. In fact, that's an example that we did earlier with the generating function. Right, that was the generating function that had a sum in it. So we know because using a generating function and applying the rules for a canonical transformation to get the transformation from the generating function, we guarantee that the transformation is canonical. We already showed that this is a canonical transformation. So let's check it now with the Poisson bracket. So the Poisson bracket method tells me that I have to evaluate the Poisson bracket. I have to do 3 of them, right? I have to do the Q's with each other, the P's with each other, and the Q's with the P's. Let me start with the Poisson bracket of Q and Q. Capital Q and capital Q. So there's only 1 degree of freedom, so there's no sum. So the Poisson bracket of Q with Q, note that it's identically 0, so I don't actually need to calculate it. But let's go ahead and calculate it anyway. So that's di capital Q by di lowercase q, di capital Q by di lowercase p, and then minus the opposite, which is di capital Q by di lowercase p, times di capital Q by di lowercase q. So, of course, that's identically 0 because partial derivatives commute. So let's say I actually evaluated these partial derivatives. So di capital Q by di lowercase q, I have to look at what my function is for capital Q. So my function is that capital Q is equal to lowercase p. So di capital Q by di lowercase q is 0. Di capital Q by di lowercase p is 1, minus di capital Q by di lowercase p is 1, the last term is 0. Of course, that gives 0. Let's try the other one. Let's try p with p. So the Poisson bracket says I have to do capital P by di lowercase q times di capital P by di lowercase p minus di capital P by di lowercase p di capital P by di lowercase q. Again, those commute, so it's identically 0. If they're identically 0, no, it wouldn't. They're always 0 between the same variables. But if I evaluate this explicitly, so di capital P is q. Capital P doesn't depend on lowercase p, so that part is 0. Di capital P by di lowercase p, again, is 0, and then the last term is minus 1. And the third one I need to check is capital Q with capital P. Di capital Q by di lowercase q, di capital P by di lowercase p, minus di capital Q by di lowercase p times di capital P by di lowercase q. Okay, so the first term, di capital Q by di lowercase q is 0, because capital Q doesn't depend on lowercase q. Second term, di capital P by di lowercase p is also 0, because capital P doesn't depend on lowercase p. The third term, di capital Q by di lowercase p is 1. And then the last term, di capital P by di lowercase q is minus 1. So 1 times minus 1 is minus 1. There's a minus sign at the front, and so you get plus 1. And so that, in fact, satisfies the conditions that we outlined above. If I do Q's with P's, in this case there's only 1 Q and there's only 1 P, right? So there's no IJ. So Q with P gives 1, and all the other ones give 0. That's a much easier way to check if that transformation is canonical. Okay, so what we've done here so far is the main result is that we've shown that if I do a canonical transformation, if I do a Poisson bracket in the capital Q's and the capital P's, I get the same number as if I do it in the lowercase q's and the lowercase p's. At least that's true if I'm doing it between the coordinates. So the plus one bracket between coordinates certainly appears to be invariant to canonical transformation. It doesn't matter in which coordinate system I do a plus one bracket of the coordinates. That leads to this easy result for checking if the transformation is canonical. But a deeper question is, if I take the plus one bracket of any two functions, does that depend on which coordinate system I'm in? So does the plus one bracket between two functions, is it invariant to canonical transformation? The plus one bracket between coordinates we've shown is invariant under canonical transformation. And that was not so difficult to show because when we evaluated that plus one bracket, we were able to use the direct conditions, which are true between specific coordinates, to simplify things. We don't expect that if we do the plus one bracket between two arbitrary functions, that these direct conditions are going to come to our rescue. So it's going to make it more complicated. So this part is truly horrible. And I'll do most of the derivation, at least to the point where it's trivial to understand the rest of it. And just painful. Okay? Okay, I'm back. Again, I'm just doing one that kicked out. And I have to assume that's my own internet. Okay, people can hear me now. Yeah, okay, so what I want to do here is I want to consider the general plus one bracket between two variables, and I want to see if it's invariant to canonical transformations. So I want to answer the question, if I take the plus one bracket between two functions u and v, and I evaluate that using the lowercase q's and the capital and the lowercase p's, is that equal to the plus one bracket of u and v evaluated in the capital Q's and P's? Because if it is, that's actually quite important. If we find that the plus one bracket between two things is what we call a canonical invariant to a canonical transformation, and remember the plus one brackets can also help us find things that are conserved. So things that are conserved in one coordinate system will then be conserved in the other coordinate system. So actually we kind of expect this to be true. Right? Remember, if you take the plus one bracket of something with the Hamiltonian and you find that that's 0, that thing is conserved. And so it would be good if that thing is still conserved after a canonical transformation. So that's the general gist of this. But the math is a little bit painful. So for reference, let's remind ourselves of u and v in the lowercase qp's. That's the sum over the degrees of freedom of di ui by di qi, di vi by di pi, minus di u by di qi, di v by di pi. Alright? That's the definition. That's in the lowercase q's and p's. Now let's do the other one. Let's do u and v evaluated in the capital Q's and capital P's. And this one's a pain. So let's start that off as the sum over the degrees of freedom I I just apply the definition, that's di capital U by di capital QI by capital V. Well, using V they're always capital, I'm not going to keep saying that. So it's di V by di capital PI minus di U by di capital PI di V by di capital QI. Now, I have four different things there, right? I have di U by, well, you can see the four different terms that I have, right? I have U's and V's partial differentiated between both Q's and P's. So I'm going to write out each one separately. So I have the sum over I. And what I'm going to do now is I'm going to do di U by di QI, right? But I'm going to write that in terms of lowercase QI's and lowercase PI's. So I'm going to apply the chain rule. So right now I'm writing only this term here. Okay? So if I break that term up using the chain rule, I have to use a new index. So it's going to be the sum over J. So it's di U by di capital QI. So that's going to be di U by di lowercase qj times di lowercase qj by di capital QI plus di capital U by di lowercase pj di lowercase pj by di capital QI. That's just that first term. That's just applying the chain rule to the. Alright, so because capital U depends on lowercase q and p, if I want to think of it that way. If I think of it that way, then when I do di U by di QI, I have to do how does the lowercase q depend on the capital Q, and how does the lowercase p depend on the capital Q? Okay? That's the first term. That multiplies the second term. The second term I write the same way. That's the sum over J. So the second term is, so it's di V by di capital PI, right? So it's going to be di capital V by di lowercase qj by lowercase qj by di capital PI plus di capital V by di lowercase pj times di lowercase pj by di capital PI. Those two terms are multiplied. Alright, the next term, so I now have a minus sign, and I have di capital U by di capital PI. Now, of course, I do the same thing again. So I have the sum over J. Now I have di U by di QJ di capital U by di lowercase qj di lowercase qj by di capital PI plus di U by the other thing it depends on, so then di pj, lowercase pj, and then times di lowercase pj by di capital PI. And that multiplies the last term, which is di V by di capital QI. So now I'm going to expand. I have di V by di lowercase qj di lowercase qj by di capital Qi plus di v by di lowercase pj by lowercase pj by di capital Qi. That's the whole Poisson bracket. So now I should multiply all these things out, right? So I have to multiply this thing times this thing. I have to multiply this thing times this thing. Okay? So if you carry out all of this, it's mathematically not so difficult, right? But it's a bit of a pain. Well, let me focus on just one of the products. So I'm going to focus in particular on the terms that have di capital U by di lowercase qj and then di v by di lowercase qj. So I'm going to focus on multiplying. So this term here has a di u by di lowercase qj. So basically I want all the terms that have u's and v's divided by di lowercase qj's. So I have one there and one here. And in the second term I have one here and I have one here. So if I write the sum out, I'm going to start way at the left here. So you can always put the sums together. So I have the sum over I and the sum over j. So my first blue term, this blue term, okay, let's put some green labels here. So I have term 1, 2, 3, and 4. All right, so I have these 4 terms. I'm going to have a 1 times 3 and a 1 times 4 plus a 2 times 3 and a 2 times 4. And that's going to be minus the same thing on the bottom side. Okay, so I only care about the things now that have lowercase qj's in it. And then you have to do the same thing for all of them. But let me do only the lowercase qj's. So the things that only have lowercase qj's on the bottom, it's term 1 times term 3. So that gives me a di u by di qj by lowercase qj by di capital Qi. That multiplies di capital V by di lowercase qj and di lowercase qj by di capital Pi. Alright, so that's these first 2 guys are term 1, these second 2 are term 3. And I do that on the bottom side as well. So then I have a minus sign. I have di u by di lowercase qj, which comes with a di lowercase qj and a di capital Pi. And that multiplies a di v by a di qj, di lowercase qj again by di capital Qi. And then it's plus a bunch of other stuff. Okay? So you can see how you can write it out for all of them now, right? You just have to keep multiplying. So you have to do, if I've done 1 and 3, but then you also have to do 2 and 3 and 1 and 4. And you have to do the same thing on the bottom. So you get a bunch of these terms. Let me focus on just this term. So these terms here, I chose them, and they all have a di capital U by di qj and a di capital V by di qj. That appears in both terms, right? So let me factor that part out. That's equal to the sum over I, the sum over j. So I'm going to factor out di u by di qj and di v by di qj. So the first term that multiplies is di lowercase qj by di capital Qi, di lowercase qj by di capital Pi, minus, on the second, the minus side, I have, the first thing I have is a di lowercase qj with a di capital Pi, and then the last term I have a di lowercase qj by di capital Qi, plus an infinity of other things. Okay? So hopefully you don't feel like I'm sweeping things on the rug. This is actually rigorous, right? Alright, so the final step is to look at this and see what it looks like. Well, if I pick out, I'm allowed to invert the summation indices, right? I can do the sum over I and then the sum over j, or I can do the sum over j and then the sum over I. But it doesn't matter which order I do the sums in, right? So if I particularly do the sum over I first, if I look at the thing in parentheses, the thing in parentheses is the Poisson bracket of lowercase qj with itself. This thing here, the thing in Poisson in parentheses, is the Poisson bracket of lowercase qj with itself, evaluated in the capital Q and capital P. You guys believe me? After I've done the sum over I, that is the Poisson bracket of qj with itself, right? Because I have di qj by di capital Q, di qj by di capital P, minus di qj by di capital P, di qj by di capital P. That's the Poisson bracket. It's also obviously equal to 0 because the partial derivatives commute. But it's also neat to notice it's the Poisson bracket. Okay? So many math later, what you find this whole thing equal to, it's now the sum over j. I'm going to get, if I do the sum over I, basically it turns that into a Poisson bracket. Right? So a Poisson bracket has a sum inside of it. So the final result doesn't have the sum over I anymore. So the final result is the term that we just did, which was di capital U by di lowercase qj multiplied by di capital V by di lowercase qj. We just found that multiplied the Poisson bracket of qj with qj evaluated in qp. And of course, we know we don't really need to put that index for a Poisson bracket between coordinates because you know the Poisson bracket between coordinates is invariant. Alright, so now if you actually did carry out the math and you did all of those, you would find the second term, you would have factored out a di u by di lowercase qj times di v by di lowercase pj. And you would have found that multiplies the Poisson bracket of qj with pj. And there's two more terms. The other term you would have factored out would have been di u by di lowercase pj di v by di lowercase pj. And you would have found that multiplied the Poisson bracket of pj and pj, evaluated in qp, to be complete. And then you would have found the last term to be di u by di lowercase pj di v by die lowercase qj, and that would multiply the Poisson bracket of pj with qj. Note that the last Poisson bracket is the opposite order of the one just above it. It's pj with qj instead of qj with pj. Remember, it doesn't commute the Poisson bracket, right? You get a minus sign if you switch the two. Alright, so we're almost there now. So we've actually already pointed out that that term qj with qj is 0. Term with pj and pj is also 0. I didn't really need to write it out. The qj with pj, that's equal to 1. And pj with qj is equal to minus 1. Right? We just evaluated those previously. So the Poisson brackets between coordinates are invariant, and so they're equal to 1 if it's a momentum with a coordinate, and it's equal to 0 the other way around. And it's equal to plus 1 when it's the coordinate and the momentum, and minus 1 when it's the momentum with the coordinate. Wow, so, alright, so then we have sum over j. So the things that are 0 I'm not going to rewrite, and then the things that are 1 I'm just going to put the sign in. So the first term I have is die ui by die qj, so sorry, die u by die qj, die v by die lowercase pj, and then the second term is minus die capital U by die pj, die v by die lowercase qj. Wow. Okay, now that is the Poisson bracket of u and v evaluated in the lowercase q's and v's. But what did we start with? Well, all the way back to the top. What we started with was u and v evaluated in the capital Q's and the capital P's. And we showed rigorously, we were just lazy to write out all the terms, but if it works for the one of the terms, it works for all the terms. Eventually, we showed that that was the same as the Poisson bracket evaluated in the lowercase coordinates. And so what we find is that the Poisson bracket of u and v evaluated in the canonical coordinates capital Q and capital P is the same as when it's evaluated in the lowercase q and p. So what we say is that Poisson brackets are canonical invariants. So it has useful properties, right? So if something is a canonical, if a Poisson bracket tells you that something's conserved in one set of coordinates, that thing's also conserved in the other set of coordinates. That's very important. It also makes it easy to evaluate Poisson brackets, because maybe the Poisson brackets are easier to evaluate in one coordinate system than they are in the other coordinate system. And if it's a canonical transformation between the two coordinate systems, then you can choose to evaluate the Poisson brackets in the easy coordinate system. All right. So I mean, I think it's good exercise for you to work out through the terms. I'm wondering if I should make this an assignment question for next week. We'll see. Maybe that's a bit cruel. All right. Any questions? All right. So the last part is the part I was going to promise to blow your mind, but it's deep and you'll have to think about it. Get rid of this little. All right. Well, the last thing I want to talk about in this chapter is infinitesimal canonical transformations. canonical transformations is transformation from lowercase letters to uppercase letters that preserves the canonical equation. I can make that a very small transformation. So, an infinitesimal canonical transformation, I could have the capital QI equal to the lowercase qi plus just a little bit. And then I can say the capital PI could be equal to the original PI plus just a small change, which I'll call delta QI and delta PI, respectively. So that's a canonical transformation. In fact, this canonical transformation is very, very close to the identity transformation, right? Lowercase q is almost equal to capital Q. Capital P is almost equal to lowercase p. So this is related to the identity transformation given by the generating function remember, we actually did one of the examples that if you take the generating function to be the sum over the degree of freedom of lowercase qi with capital Pi, if you take that as the generating function, the transformation that you get is the identity transformation. You get that capital QI is equal to lowercase qi, and you get that capital Pi is equal to lowercase pi. Okay, so that generating function, the sum of qi with capital Pi, gives the identity transformation. We showed that. And we showed that it's canonical. Well, obviously it's canonical because it doesn't do anything. Okay? This is a transformation, canonical transformation of the second type, right? It mixes lowercase q's with uppercase p's. So that's the identity transformation. So I want a transformation that's like almost the identity transformation. I want it to change a little bit. I'm going to have it change just a little bit by some function g. So epsilon, some small number. And then I take a function that's g and that depends on the lowercase qi's and the capital Pi. Alright, so I'm making my generating function f to be the identity transformation plus epsilon times a little bit. This is a type 2 transformation, right? So for type 2 canonical transformation, we have, so this is a transformation that depends on the lowercase q's and the upper p's, and the capital P. So the ones we don't know are the lowercase p's and the capital q's. So the canonical transformations for type 2 are given by lowercase pi is found by taking by lowercase qi. That's why I did that example in the summary earlier. And then, sorry, the other one we want is capital QI. That's given by di-f by lowercase pi. But I know f, right? So I can actually do this derivative. So I do the derivative of f with respect to lowercase qi. And that's going to pick out the term in the sum where I really should have done the sum over j's maybe just to be less confusing here. So it's going to pick out the term where I equals j. So it's going to give me pj. And then it's going to be plus epsilon times di g by di qi, whatever that function is. Similarly, if I do di qi by di lowercase pi, sorry, that's capital Pi. Because f depends on lowercase q and capital P. If I do di half by di pi, well, it's the same thing, right? I'm going to pick out the term where I is equal to j, so that's going to give me the qi. And then I'm going to get plus epsilon times di g by di capital Pi. And so if I compare this with what I said at the top there, for an infinitesimal canonical transformation, then I can identify that delta qi, the thing that I just put in up here, for that given generating function, the delta qi would be equal to epsilon times di g by di lowercase qi. And then the delta pi there's a minus sign in the notes here. All right. The delta pi is minus epsilon times di g by di qi. Sorry, let me start over again. I look at my equations here. The first equation tells me that capital Pi is equal to lowercase pi minus epsilon di g by di qi. And if I look at the second equation, I have qi is equal to lowercase qi plus epsilon di g by di capital Pi. Because I want to put the big letters on the left and the small letters on the right, just as I do up here. And so then I get delta qi. Now if I just identify it, delta qi is epsilon times di g by di pi, and delta pi is minus epsilon times di g by di qi. Sorry for being confusing. It's already not easy to understand. Alright. Now I'm actually going to do a little trick. A nasty little trick here, but I'm going to look at the first term here. So delta qi, just going to rewrite it, that was equal to epsilon di capital G by di capital Pi. So that's equal to epsilon times di G by di. But now instead of capital Pi, I'm going to say that capital Pi was equal to lowercase pi plus a delta pi, right? That's the transformation. So capital Pi is almost equal to lowercase pi. It's just lowercase pi plus delta lowercase pi. So the derivative of g with respect to capital Pi is almost equal to the derivative of g with respect to lowercase pi. That's a little bit nasty. Mathematicians would frown a little bit. But it's actually exact, right, in the infinitesimal case. It's a little trickstery to change a capital letter into a lowercase letter, which is true when the limit of epsilon equals to 0. Alright. So after my nasty trick here, I have di qi is equal to epsilon of di g by di lowercase pi. Now if you remember things about Poisson brackets, you might remember that if I take the Poisson bracket of something like g, or if I take the Poisson bracket of qi with g, then I get di g by di pi. That's one of the properties you have to prove. It's actually quite easy to prove. And so then similarly, the delta pi that we had on the previous page, that was equal to minus epsilon di capital G by di lowercase qi. And again, that's equal to epsilon times the Poisson bracket of pi with g. So again, if you take the Poisson bracket of pi with g, you get di g by di qi. That's actually very easy to prove. So we've defined a new canonical transformation where capital Qi is equal to lowercase qi plus epsilon times the Poisson bracket of qi with g, and capital Pi was the lowercase pi plus epsilon times the Poisson bracket of pi with g. And so that is actually an equation that we saw in the last chapter at the end, where we were discussing how you could do Poisson brackets of conserved quantities to find the transformation that's the symmetry that's related to that quantity being conserved. Remember, there's a symmetry in the Lagrangian. There's a quantity that's conserved due to that symmetry. That's the Noether's theorem. It's not always obvious how to find the transformation that corresponds to a conserved quantity. We found that by taking Poisson brackets of the conserved quantities with the coordinates, we could find the coefficients for the transformation of those coordinates that correspond to that symmetry. And the equations that we found were exactly this, where G was the conserved quantity. So we did the example, for example, of angular momentum, the Z component of angular momentum, and we found that the transformation that you get if you use, instead of G, the Z component of angular momentum, is a rotation about the Z axis. And then he threw out this term that you might have heard in quantum mechanics, that angular momentum is the generator of rotation. It's because you can use the angular momentum to generate the transformation that leads to angular momentum being conserved. Okay, so now consider the case where G is the Hamiltonian. So we've shown that this particular transformation is actually canonical, right? So consider the case where G is the Hamiltonian. That means that Qi is equal to the original Qi plus epsilon times the Poisson bracket of Qi with the Hamiltonian. And similarly, capital Pi would be given by the original lowercase pi plus epsilon times the Poisson bracket of pi with the Hamiltonian. But what happens when you take the Poisson bracket of something with the Hamiltonian? You get the time derivative of that thing. So that's equal to qi plus epsilon. Instead of writing qi dot, I'm really going to write it explicitly as dqi by dt. And so then the epsilon times pi with h, so that's pi plus epsilon dpi by dt. And we also saw that the Poisson bracket of the coordinate with the Hamiltonian basically gives you the canonical equation, right? So q with h, qi dot is the Poisson bracket of qi with h. So that's actually very, very interesting. So we're using the Hamiltonian to generate a transformation, an infinitesimal canonical transformation. So what is that transformation? Well, this transformation here takes the qi, the lowercase qi, and it adds a little bit of dqi by dt. So capital Qi is just lowercase qi a little bit later. Same with capital Pi. I'm going to write that as a sentence. The Hamiltonian generates the canonical transformation that moves the canonical variables through time. And that really should blow your mind. The Hamiltonian generates a transformation. Mathematically, we can make any function of the canonical variables generate a transformation. The specific transformation that the Hamiltonian generates is the transformation of taking the variables through time. It's telling us how the variables change with time. So there's a canonical transformation that is to take the variables and propagate them through time. And that's really remarkable. And that, again, ties into this whole concept of energy and time. So you have to reread the notes and go through all the derivations. And I would recommend you reread the section on Poisson brackets and symmetries to really get a grasp of this. But it's really, I think, a very deep understanding of it. I think it's amazing. Okay. Any questions about this? Okay. So if there's no questions, that's it for now. Next week we'll look at the Hamilton-Jacobi equation, and maybe we'll start on field theory if we get there. Okay.